Now we're going to look at limits at infinity. So instead of evaluating a limit where the result is infinity, we're going to say what happens as I approach positive or negative infinity for my x value. And what that results in is a horizontal asymptote if one of these two things is true. If, as I approach infinity from either the left or right side, if my limit approaches a specific value, that means I have a horizontal asymptote. So our first fact, our main fact that we're going to be looking at as we evaluate mostly rational functions here, is I'm looking at if I approach the limit of infinity from the left or right side of some constant over a rational expression, that has to be equal to 0. Right? And that kind of makes sense. If I think about a number like 1 over infinity, right, where I'm substituting in infinity for x, right, that's like 1 over the biggest number you could possibly think of. And if I make my denominator huge compared to some little constant on top, realistically, I'm getting a number as close to 0 as possible. That's going to be true for negative infinity as well, right? So if I'm looking at 1 over negative infinity, again, that means I'm looking at a really, 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 really small number because it's negative, but I'm still getting somewhere close to 0. I'm just coming up to 0 from the negative side, right? Rather than going down towards 0 from the positive side, but I am still approaching 0. So how do I evaluate a limit at infinity? We can try direct substitution, but it's going to give us some problems. So let's see. If I was to just plug in infinity here, right, I get 2 times infinity to the power of 4 minus infinity squared plus 8 times infinity over negative 5 times infinity to the power of 4 plus 7. We can only assume that infinity to the power of 4 gets even bigger, multiplied by 2 even bigger. I have an infinity. I'm subtracting an infinity from that. I'm adding 8 times infinity, which is still just that. I get a negative infinity on the bottom because I'm multiplying by negative 5. Plus a 7, which really is pretty arbitrary, is just going to include that infinity. And you might think, okay, well, these things add together. Do they cancel out? What happens here? We have too many rules at play here. Is this 2 times infinity on the top, right? Is it 0? Is it 1? What it is it's an indeterminate form, which means that I can't evaluate it. There's too many different odd rules going on at play, right? Zeros and infinities cause us problems. Sometimes we can work with them when there's enough other information, but if they're all I have, I can't really do a lot. So I'm not going to direct substitute for limits at infinity. I'm going to use that rule above instead. I'm going to try to get as many fractions where I have 1 over infinity as possible. And I'm going to do that by factoring out x. So we're going to factor out the largest power of x that we can. Specifically from the denominator, and we'll see in a bit why. I'm going to factor the top and the bottom, but I'm seeing this x minus 4 here, and I'm going to make sure that I'm factoring an x minus 4 out of everything. So I'm taking the limit as x approaches infinity of, if I factor an x to the 4 out of this numerator, well, I pull it out of the 2x to the 4, I get a 2. When I pull it out of an x squared, I have to take 2 extra x's out, so I'm at an x to the minus 2. When I factor it out of just x, I'm at an x to the minus 3, right? I could always distribute this back in and turn those powers back into what they used to be. I'm going to do the same thing on the bottom. I'm going to get a negative 5, which is just nice, plus a 7x to the negative 4. So this is great. I have some common factors. I can cancel those out. I now don't have to worry about that. And what am I left with? Well, I'm left with 2 minus 1 over x squared, if I rewrite that negative power as a denominator, plus 8 over x cubed. And then on the bottom, I have a minus 5, and then I have a 7 over x to the 4. Now remember, with limits, I can break these apart and I can evaluate the limit of each of these terms independently, and I can evaluate the limit of the numerator and the denominator independently, right? We had all those limit rules. So what's going to happen is all of these, and let's do a little bit of highlighting, this and this and this are all going to meet this rule, right? Where I have something over x with some power, could be 0, could be 1, could be anything, as long as it's not a fraction, right? As soon as we get into square roots, things get messy. But all of these are just going to approach 0. And so when I evaluate the limit, I get a 2 minus a 0 plus a 0. The limit of a constant, minus 5, is minus 5 plus a 0. And so the limit of this thing, while the infinities led us to believe maybe it was 0, maybe it was infinity, maybe it was 1, who knew what was happening here, turns out this thing actually approaches negative 2/5. And what that means is that if a limit at infinity on one side or the other, when we do horizontal asymptotes, we're going to check both. But this tells me that there's a horizontal asymptote at y equals negative 2/5. Right? This is my y value that we're finding the result of. And what this is really saying is that as I look at this graph and this graph gets closer and closer and closer and closer to positive infinity, this thing really is trying to approach a specific y value of, it was negative 2/5. Let's do that again. As I get closer and closer and closer to infinity, this thing is really, really, really getting close to a value of negative 2/5. And so we have a horizontal asymptote, at least from the right side. We're going to check both later on just to make sure that we are sure we have only one horizontal asymptote. Maybe we have more. So let's look at something like this. Still a rational function. Same thing is going to kind of hold true here. I want to approach this limit as I approach negative infinity, which is going to work exactly the same as positive infinity. And I want to factor out the largest factor of x I have in the bottom. So I see that 2x, so I pull out an x. Leaves me with 5x to the negative 1 minus 2. I need to be able to pull out a factor of x on the top, but it also needs to be a factor of x outside of the radical. So first things first, I'm going to take the square root. I'm going to pull an x squared out of these two terms, because that's the biggest power I can anyway. 3 plus 6x to the minus 2. Now, when I take the square root of that x squared, it's going to be great, right? The square root of x squared is just x. Then I have the 3 plus 6 over, I'll rewrite that as the fraction just so we can get a better view. 6 over x squared. On the bottom, I have x times the 5 over x minus 2. Things are great, except I need to be very careful about this. When I take the square root of x, it's actually the absolute value of x, square root of x squared, right? Because I don't know, if I put a negative number into that x squared, it's still going to spit out the same result because of that squared sign. So remember that the absolute value of x squared looks like one of two things. Either it's a negative x, and the sign has to change because of these absolute value bars, or it was already a positive x, and so nothing has to change. The nice thing is I'm already telling you what x's we're looking at when I tell you about what we're approaching. So because I'm taking the limit as x approaches negative infinity, that means I'm going to replace this x with a negative x. If I was to take the limit as x approaches from positive infinity, that's where I would replace x with just x. Because I know that I'm working with really, really big x values. I can assume they're positive safely. So be super careful with that. The square root of x squared, if I'm pulling something out of a radical, I have to consider the sign of x that I'm working with. Things still cancel. Everything's still good. I can say this cancels with this. It's just leaving a negative in its place. So the limit, as x approaches negative infinity, is now going to be negative 1 times the square root of 3 plus 6 over x squared. And then on the bottom, 5 over x minus 2. And then I evaluate the limits of all of these things. And so I get the limit, as x approaches negative infinity, of negative, we're going to evaluate. I just get negative 3 plus 0, right? I can still do all of these things independently. 0 minus 2. And so I get a negative root 3 over negative 2, which means this thing actually approaches positive root 3 over 2 on the left side. So I have a horizontal asymptote at y equals root 3 over 2. If I really quickly evaluated this limit from the right side as well, as I approach positive infinity, let's do that. So when we're finding a horizontal asymptote, we should check both. It's going to be the exact same thing. I'm going to factor out that power of x squared. 3 plus 6 x to the negative 2 over x, 5x minus 1 minus 2. The only thing that changes here is when I take that square root of x squared outside of the radical, because I know I'm approaching positive infinity values, I'm going to be worried about this replacing x instead. X gets replaced with an x because I know it's already positive. And so I still have a 3 plus 6 over x squared inside the radical. I still have a 5 over x minus 2 inside the denominator. These x's cancel out. There's no negative kicking around anymore. So same thing, the limit of root 3 goes to root 3. The limit of 6 over x squared goes to 0. The limit of 5 over x goes to 0. Negative 2 goes to negative 2. And so now I have that negative still on the bottom, the positive root 3 on top. And so this thing tells me that this graph actually has two horizontal asymptotes. I have a horizontal asymptote at negative root 3 over 2 on the right side. I have a horizontal asymptote at positive root 3, 2 over on the left side. And that just means my graph near the edges does two different things. I don't know what this graph looks like in the middle, right? But I know that as I approach on the left side, I got those backwards. As I approach on the left side, I'm going up to positive root 3 over 2. And as I approach on the right side, I'm going over to negative root 3 over 2. So let's look at a couple of examples where I just want to find all of the asymptotes and use my definitions of limits to justify them. So here's a function, y equals x minus 3 over the square, or over x squared minus 4. So remember, I'm looking for vertical and horizontal asymptotes this time. Math 30 would tell me to just expand this, factor the bottom here into an x plus 2 and an x minus 2. And then it's going to tell me a bunch of things, depending on what you remember. Number 1, it's going to tell me that we have a vertical asymptote at x equals negative 2. It's going to tell me we also have a vertical asymptote at x equals positive 2. It's also going to tell me I have a horizontal asymptote at y equals 0. And that's because the degree of the numerator is less than the degree of the denominator. Right? Because that's all we had before. That's the only way we could find a horizontal asymptote. And these are from my NPVs. I have an NPV at x equals negative 2. I also have an NPV at x equals positive 2. And neither of those are factors that are canceling out. All right. I also know that I have an x-intercept at positive 3, but that's not helping us here at all. So now I'm going to use limits to tell you why all these things are true. First thing, if I want to talk about the vertical asymptote at x equals negative 2, let me prove it to you. So vertical asymptote at x equals negative 2. Because I know that a vertical asymptote means it's an infinite limit, it means I need to approach it from the left and right side. Again, as long as one of those things approaches infinity, it technically is a vertical asymptote. I want you to check both. So I'm going to approach negative 2 from the left side of x minus 3 over x squared minus 4. So I plug in a value of negative 2. I get negative 2 minus 3 on the top. I get a number that's slightly smaller than negative 2 on the bottom. Let me include that sign. And because I'm squaring it, now it's going to be something that is ever so slightly bigger than 4, because it was something to the left of 2. So I get a -5 on top. I get something that's actually slightly bigger than 0 on the bottom, because that negative sign cancels out, and I have a number larger than 2 in the end of the day. And so this limit of the left side of -2 actually approaches negative infinity. Again, enough to prove that it's a vertical asymptote, but I want you to keep going. Let's check from the right side of -2. I plug it in, direct substitution. Because I'm doing that one-sided limit, direct substitution doesn't cause a problem. Now, because I'm something slightly to the right of 2, -2, it's actually a number that's going to be smaller than 4 at the end, right? It's like taking 1.999 and squaring it, right? It's only going to give you 3.999. So when I subtract 4, I'm overall negative on the bottom. So I get a -5 over a slightly negative 0, which means this thing actually approaches positive infinity on the right side. Let's look at our other vertical asymptote really quick. It's going to be the same kind of idea. I'm at +2. I'm going to look on the left side of +2 of x minus 3 over x squared minus 4. Plug things in. I get a -1 on top. Something slightly lower than 2 squared subtracted 4 is going to give me a negative value. So this thing approaches positive infinity from the left side. And it's going to approach negative infinity from the right side. Right, I get a 2 minus 3. I get a number bigger than 2. Square it, I subtract 4, which means I get a positive value on the bottom. Negative on the top tells me I approach negative infinity. So there's my justification for my 2 vertical asymptotes. Now I get to my horizontal asymptote, and I just need to check where is it approaching when I go toward positive and negative infinity in terms of x. Well, I'm going to check both of those infinite limits here. So as I approach negative infinity of x minus 3 over x squared minus 4, again, I can't just substitute in an infinity here. I need to do a little bit of work first, right? Because I don't know about that indeterminate form. So I factor out the largest power of my denominator. So I'm going to factor out an x squared. It's going to give me a 1 minus 4 over x squared. I'm also going to factor an x squared out of the top because I want it to cancel out completely. I know I don't have an x squared on the top, but it's going to give me a 1 over x minus 3 over x squared. But that's fine. That leads me to a 0 minus 0 on the top, a 1 minus 0 on the bottom, which isn't indeterminate form anymore because I have a value on the denominator. Right? And I'm just evaluating, I'm using that rule. I'm saying I know the limit of any fraction, rational function, constant over x to some power is 0. And I get 0 over 1, which means this thing approaches 0 on the right side. I can have 2 different limits. They don't have to be in agreement, but I should check both sides. So let's check negative infinity as well. It's going to be the exact same process. I'm going to factor an x squared out of both. 1 over x minus 3 over x squared. 1 minus 4 over x squared. They cancel out. The same rule applies with a negative infinity as it does a positive, so I get to the exact same result. 0 minus 0 over 1 minus 0. The only time we'll really see that sign change is with those radicals for us, for our intents and purposes. And so this thing has a horizontal asymptote at y equals 0. It has a vertical asymptote at x equals 2. And it has another vertical asymptote at x equals -2. And so that's how limits at infinity and infinite limits can tell us about some of our asymptotes.